All right, here we go. This is going to be part 2 of data analysis. We're going to breaking this into 3 parts. So start out with just some measures of central tendency, right? You all know this already. Mode is the score that occurs most frequently. Mean is the arithmetic average, right? What we all think about when we think about average. And median is the score that divides the distribution in half, right? So the mode is going to be, right, the score that occurs most frequently is 5, right? We've got 5 occurs the most. The arithmetic average, right, is going to be which we've got to add them up and then divide by the number. So we've got 0 plus 1 is 1, plus 2 is 3, plus 3 is 6, plus 5 is 11, plus 5 is 16, plus 5 is 21, divided by 7 numbers, so the mean is 3, right? We just add them up, divide by the number of numbers. Median is the score that divides the distribution in half. That was my son making that noise. Median is the score that divides the distribution in half, so that would be 3, right? It's the middle score. We've got 7 numbers. You look at the fourth number, the one in the middle, is going to be 3. Again, you all know that. I know that. All right. Then we've got some measures of variability. And number 1, we've got range. So often, you might report the median and or the mean and or the mode. Usually the mean score, right, is what we're going to report depending on the type of data we have. And then we might also report the range. And the range is the difference between the highest and the lowest scores. So here we've got this. So we could either report the range as the numbers ranged from 14 to 92, and then we might also report actually the difference between them. So the range was 92 minus 14, which is 78, right? Was the range of numbers. Even more importantly, though, is the standard deviation. And the standard deviation is the average amount the scores deviate from the mean. And this is really important. And anytime you report the mean in a research article, you always have to report the standard deviation. And so we're looking at the average amount the scores deviate from the mean. So let's look at these two columns, column A, column B. All right. The mean score in column A is 50, right? We can add them up, divide by 5, we get 50. The mean score in column B is also 50, right? So it's the same mean score for both groups. However, they're very different, right? A lot of times what we're doing in research, what we're doing in science, what we're doing with all of our data collection is really based on probability. So, and what's the probability, right? If we're talking about therapy, what's really important isn't necessarily how well our groups did. It's, can you take that information and then think about how your client might do. So if these were the 5 scores, and we've put them in order here, but from lowest to highest, but if these were the 5 scores, how well could you predict what your client would get? Well, you couldn't, right? Maybe they get anywhere from 0 to 100. So even though the mean is 50, they could fall anywhere between that 100-point range. However, right, if we're looking at group B, right, and these were all the scores put in order, I would feel pretty confident that, my client then would probably fall somewhere between 45 and 55, right? That they'd be somewhere because they're all grouped together. So the average amount the scores deviate from the mean is really important. You can't just report the average score. You've got to report how different scores are from the average as well, right? All right, let's talk about normal distribution now. And I'm going to want you to know some of this for the test. So 68% of all test takers will fall within 1 standard deviation of the mean. 95% will fall within 2 standard deviations of the mean. And about 99.7% will fall within 3 standard deviations of the mean. Now, what does that mean? And we'll look at a couple. This is more of a simplified chart, right? So here's our nice standard deviation, right? We're going to say that the person who gets, the exact average score, and the cool thing about a normal distribution is it groups the scores and computes them, and so the middle score, the mean, the median, and the mode are all right here. So the middle score, the mathematical average score, and the most common score are all the same number. So if you go out by standard deviations, right, 68%, 34% plus 34% will fall between -1 and +1 standard deviations of the mean, right? And if we look at standardized scores, so usually IQ tests, a lot of our language tests are going to have that average score will be given a score of 100. People who are 1 standard deviation below the mean will have a score of 85. People that are +1 standard deviation above the mean will go by 115. And scores on the test are going to go by 15s according to standard deviation. So 1 standard deviation above the mean receives a 115. If you're 2 standard deviations above the mean, you get a 130. If you're 3 standard deviations above the mean, you're going to get a 145, right? Because we're just going by 15s. If you're 1 standard deviation below the mean, you get an 85. Again, going by 15s. If you're 2 standard deviations below the mean, you get a 70. If you're 3 standard deviations below the mean, you get a 55, right? We're going by 15s. So again, about 68% of all test takers are going to fall within 1 standard deviation of the mean, either plus or minus. Going out, about 95% of test takers are going to score within 2 standard deviations of the mean, right? So 95% of the people taking the test are going to score within 2 standard deviations of the mean. Right? Now let's get a little bit more complicated here. Kind of the exact same thing. We're just adding in a little bit more, right? So we're getting a little bit more precise here in the numbers. So again, 68% about are going to fall within 1 standard deviation of the mean, plus or minus. Here's that standard score again, right? So we've got that 100. We've got, so that person at 50%. So now we've got percentile ranks. So the person in the middle has a standard score of 100, is at the 50th percentile rank. All right. Now, we've got the person at +1 is going to be at about somewhere between 84 and 86 percentile rank. Is at +1, they get a 115. Remember, we go by 15s. The person at +2 is about 98% percentile rank. They get a 130, and we're not going to worry about 4. We're only going to go out to 3. The person at +3 percentile ranks, remember we said gets a 145, or +3 standard deviations. I'm sorry. And then down, right? -1 gets an 85. -2. Right, I need that little block to move. -2 gets a 70 on the test. -3 gets a 55, right? So, and then, so if we're looking at percentile rank, right? If if somebody has a 130 IQ, right, that person is in the 98th percentile. So their IQ score is higher than 98% of the population. And they're at +2 standard deviations. So knowing the standard deviation then lets us also know the percentile rank and their standard score. So that, again, if you get an 85, if you have a client who has an 85 standard score, right, which is down here, you know that they're in the 16th percentile rank, and, right, that they are 1 standard deviation below the mean. And that they're still well within average range, right? So average range is 1 standard deviation below to 1 standard deviation above, right? So if we're talking to parents about their child, and let's say he's in the 30th percentile rank, right? They're like, oh my gosh, he got a 30%. You can say, no, he's still well within the average score. Like, he's not even close to being outside the average. So it's once we get below 1 standard deviation of the mean, that's when we get to, lower than average, and maybe talking about somebody who has a disorder or has a lot of difficulty doing, whatever that task is. So I hope that made sense. Okay, now, right, those are all descriptive statistics. So everything we've been talking about, whether we're talking about the mean, the median, and the mode, whether we're talking about range, standard deviation, right, we're really just saying, here are the raw numbers, here's the average, here's how the person ranks compared to other people taking the test, right? But we're not really doing anything to see, all right, what is, what conclusions can we draw? Now here we can, right? We can draw some conclusions here. So we're starting to get into inferential information. So inferential statistics allow us to draw conclusions about the population from which the sample was taken. And they rely on probability. So again, this is all about probability, right? What are the chances that it was really the treatment that made the change, or that the change in the people was just due to random chance, right? People are going to change all the time, every day. Was this just random chance that they changed or got a higher or lower score, or was it truly due to the treatment? And how much of a difference do we have to have, right? So here, let's say we've got 5 participants. They take a pre-test. They then take a post-test, right? And maybe these are, number of moments stuttered, or articulation errors, or whatever, right? Okay, they all did, they all did a little bit better, but is that significantly different? Is that just due to random chance, or was that due, is that something real, right? So one way to think about inferential testing and all of this is something due to chance or not due to chance, right? Let's see if we can go, let's go to that random number generator again. And we're going to go to the coin flipper. So we're going to flip some coins. We're going to flip them 10 times, and it gives you a million different kinds of coins. We're going to use a coin from the Roman Empire. What the heck? All right, we're going to flip it 10 times. Ready? All right, so 10 times. These are heads. These are tails. So let's see. Let's make this a little bit smaller here. What did we get? We got 1, 2, 3, 4. We got 5 and 5. That is so random that we got exactly 5. All right, this is cheating on me. Hold on. Let's try that again. Let's do it one more time. Okay, now we do it again. We get 1, 2, 3, 4, 5, 6. And then 1, 2, wait, no. We got 1, 2, 3, 4, 5, 6, 7 heads and 1, 2, 3 tails, right? So that time we got 7 heads and 3 tails. So should we then write up a paper and publish the fact that when you flip a Roman coin 10 times, 70% of the time it's heads and 30% of the time it's tails, right? Well, no, of course we can't do that because that was just random, right? But if our clients are making changes, right, how do we know that's not just random change too? So what the inferential tests allow us to do is to say, all right, is the change large enough that we can say it was probably a true change, or that it was just due to random chance, right? There's just a random chance that coin flipped and ended up 7 heads and 3 tails, and that, it's just random chance that my clients, improved a little bit on their post-test, right? So how do we know? And one thing that's important here is going to be sample size. So the more people you have in your sample, the more like the population it is, right? So there's always variation between the sample and the population. As your sample size increases, the sampling error decreases, right? So when we're talking about sampling error, let's say I want to get all the 3-year-olds in the United States who have childhood apraxia of speech. Well, I can't get them all, right? So let's say I get 20 in my sample. All right, I've got a 20 sample size, but I'm going to have a lot of error there, right? Because my sample size is not the whole population. So let's say I get, in my next study, I get 100 kids who have childhood apraxia of speech. All right. My sampling error will be less because my sample is going to be more like the whole population with 100 kids in it than it was with 20. So sampling error is just about, okay, it's kind of like your sample is kind of like the population, but we know that it's not the population, and we know there's going to be some error. So the more people you can get, the lower that sampling error is. All right, so when we are doing our inferential tests, we're testing the null hypothesis. All right, remember that the null hypothesis is that there's no difference between group A and group B, that there's no difference between knowledge of a freshman and knowledge of a senior, that there's no difference in the height of males and females, whatever. The null hypothesis is that there's no difference, and that any difference we see is just due to random chance, right? Most of what we do in research is to try to reject the null hypothesis and say, no, there really is a difference between freshmen and seniors in their knowledge about speech-language pathology. That there really is a difference between people who before they've had therapy and after they've had therapy, right? So we're trying to reject the null hypothesis. We're trying to say, yes, there is a difference between things. So the goal of the researcher is to reject the null hypothesis and accept the research hypothesis, right? So the research hypothesis is one is better than the other. One therapy is better than the other. One drug is better than the other, right? One thing is better or different from something else. But how do we know if we can reject the null hypothesis? How do we know if the difference that we see is large enough that we can say there's a true difference and not some random difference by chance? So what we're going to use tests of significance. These are statistical tools that allow us to make the judgment about the null hypothesis, to tell us if the difference between means in the groups is large enough to conclude that the difference was probably, I should add probably there, was probably due to treatment and not to chance, right? We can never say for sure that something is proven or that we're sure about something, but we can say that something was probably because of treatment or probably due just to random chance. So what we're going to do as researchers is to accept the probability level that we will be incorrect in rejecting the null before data are concluded. So what does that mean? So the probability level, and in research we call that the p-value. It's the probability of observing a test statistic. Think of it as the chances of getting a certain result. So the p-value is the probability that any differences between groups are just due to chance. All right, so that, right, the difference in knowledge about speech-language pathology for students starting the Intro to Communication Disorders class is the same as the knowledge about speech-language pathology of students who graduate with a degree in CSD, right? That would be the null hypothesis, right? There's no difference between those beginning the intro class to those that graduate with a degree. So in communication disorders and in most healthcare fields, we're going to set our p-value at 0.05. And so 0.05, think of that as 5%. And so that means the probability that the differences happen by chance is 5% or less. So that 0.05 means that there's a 5% chance that there's just a random difference, and there's a 95% chance that the difference was due to treatment, right? If we get that level of confidence that we can be 95% sure that treatment caused the change and not just random change, we're going to be able to say that yes, we think treatment caused the difference. But if we're only 94% sure and p-value is 0.06, meaning there's a 6% chance that the change in groups or difference between groups was just random luck, then we can't say there was a difference. All right, so p-values at or below 0.05 are said to be statistically significant. There's only a 5% chance that the outcome would occur if the null hypothesis was actually true, right? So there's only a 5% chance that the null hypothesis is true. We've got a 95% chance that the treatment really did work. Okay. So we're going to end up here just a couple more slides. So we're going to talk about rejecting the null. Actually, let me stop here. I want to add something to that. So let's go ahead and stop here with our part 2, and we will start part 3 thinking about rejecting that null.